While the world celebrated the end of the Second World War, a small group of physicists at Oak Ridge were already looking toward the next great frontier of the atomic age. In May 1945, Eugene Wigner and Alvin Weinberg penned a memo that would become the foundation for a new kind of power, one that didn't rely on solid fuel rods. Eugene Wigner, a Nobel laureate and the man who designed the first large-scale plutonium production reactors, saw thorium as the ultimate sustainable fuel source. But it was Alvin Weinberg who would become its most persistent champion. For him, the liquid fuel reactor wasn't just a technical curiosity, it was a moral imperative for safe, abundant energy. The concept was deceptively simple. Instead of solid pellets encased in metal, the fuel would be dissolved into a liquid and pumped through the reactor. This fluid nature promised inherent safety. If the reactor overheated, the fuel would naturally expand, slowing the reaction without any human or mechanical intervention. The path to proving this concept began with a program that sounded like science fiction: the U.S. Aircraft Nuclear Propulsion Program. The goal was to build a strategic bomber that could stay aloft for weeks at a time, circling the globe without ever needing to land for fuel. To power a jet engine, the reactor needed to operate at incredibly high temperatures, far beyond what conventional water-cooled reactors could handle. The solution was a molten salt reactor. Because fluoride salts don't boil until they reach thousands of degrees, they were the perfect medium for a high-performance engine. The ARE was a marvel of 1950s engineering. It was small, lightweight, and used a mixture of sodium and zirconium fluoride salts, carrying uranium-235. In 1954, in a remote corner of Oak Ridge, the team prepared to switch on the world's first operating molten salt reactor. It was a moment of immense tension and hope. The experiment was a resounding success. The ARE reached criticality and ran at a peak temperature of 1,500 degrees Fahrenheit, a record that remained for decades. For 100 hours, it demonstrated that a liquid fuel reactor could be stable, powerful, and remarkably responsive to throttle changes. The physics was proven. But the world was changing. The development of ICBMs made the nuclear-powered airplane obsolete before the prototype could ever leave the drawing board. In 1961, President Kennedy officially canceled the nuclear aircraft program. Millions of dollars and years of research were suddenly at risk of being lost. Weinberg, now the director of Oak Ridge, refused to let the technology die. He realized that the same features that made it work for a bomber made it perfect for civilian power. He envisioned a future where molten salt reactors, fueled by abundant thorium, could provide carbon-free electricity to every home in America for thousands of years. With his characteristic persistence, Weinberg redirected the lab's resources. The era of the atomic airplane was over, but the age of the thorium breeder was just beginning. By the early 1960s, the dream of the atomic airplane had faded, but in its place, a more ambitious vision was taking shape: the molten salt reactor experiment. Alvin Weinberg had successfully convinced the government to scale the ARE technology into a dedicated civilian power experiment. This would be the definitive test of the liquid fuel concept. The fuel was a sophisticated cocktail of fluoride salts. Dissolving the uranium directly into the liquid allowed for a reactor that could be refueled and potentially cleaned while running. But containing this glowing salt at 1,200 degrees Fahrenheit was a massive challenge. Traditional steels would corrode within weeks. The solution was a revolutionary new alloy, Hastelloy N. Developed specifically for the MSRE, this nickel-based superalloy was engineered to withstand the extreme combination of intense radiation and the corrosive nature of molten fluoride salts. The construction was a masterclass in precision engineering. Every weld and every valve was a first-of-its-kind component in a system that promised to revolutionize how we power civilization. On June 1, 1965, the MSRE achieved its first criticality. It was the beginning of an era of unprecedented stability in nuclear research. For the next 3 years, the reactor ran primarily on uranium-235. It demonstrated high availability and a remarkable ability to follow load changes automatically. It was the steady hand of the nuclear age. But the ultimate goal of the MSRE wasn't just to burn uranium. It was to prove that it could run on the very fuel it was designed to breed, uranium-233. In October 1968, history was made. The MSRE became the first reactor in the world to operate on uranium-233. The thorium cycle had officially been closed in an operating power system. However, the MSRE was what engineers call a kernel test. It was designed to prove the reactor and the materials, not the full chemical processing loop required for a true breeder. While they demonstrated they could recover uranium using fluoride volatility, it was done in batch mode. The continuous, real-time extraction of protactinium remained a theoretical target for the next stage. Despite this, the material results were a triumph. Hastelloy N and the graphite moderator blocks had survived conditions that many experts believed were impossible to manage. The MSRE generated a mountain of data, foundational research that lay dormant for decades. Today, that data is the bedrock upon which every modern thorium startup is built. From flybe energy to terrestrial energy, the lessons of Oak Ridge are being applied to a new generation of designs aiming to finally complete what Weinberg started. While the molten salt dreams of Oak Ridge faced uncertainty, a different kind of thorium experiment was reaching maturity. In 1977, the world's first commercial-scale thorium breeder began operation at Shippingport, Pennsylvania. It was a massive industrial endeavor that combined decades of nuclear expertise into a single, high-stakes project. The project arrived at a time of deep national anxiety. The 1973 oil crisis had exposed the vulnerability of the Western energy grid, and the search for a truly sustainable domestic fuel source had become a matter of national security. Shippingport was already a legend in nuclear history. It had been the first full-scale nuclear power plant in the world. Now, it was being repurposed for the ultimate challenge, proving that thorium breeding could work on a commercial scale. The site was chosen for its existing infrastructure and strategic location within the nation's emerging nuclear power network. The project was the personal priority of Admiral Hyman Rickover, the father of the nuclear navy. Rickover was a hard-driving pragmatist who saw the thorium breeder as the key to long-term American energy independence. He personally oversaw the technical details, demanding a level of precision that remains legendary in the history of nuclear engineering. Unlike the molten salt designs, the Shippingport light water breeder reactor aimed to adapt existing pressurized water technology. It was a bridge between the present and the future of nuclear power. By using light water, the project hoped to create a technology that could be easily adopted by the existing fleet of reactors. At the heart of the reactor was the seed and blanket core. A central seed of fissile uranium-233 provided the neutrons, while a surrounding blanket of fertile thorium captured them to create new fuel. This innovative geometry was the key to achieving a positive breeding ratio in a thermal spectrum reactor. This arrangement maximized the neutron economy. Every neutron was a precious asset, and Rickover's engineers designed the geometry to ensure that thorium capture was as efficient as possible. The goal was to reach a point where, for every atom of fuel burned, more than one new atom of fuel was created. For 5 years, from 1977 to 1982, the reactor operated with the precision and reliability that were the hallmarks of Rickover's projects. It ran for more than 29,000 effective full power hours. The plant became a symbol of industrial stability, proving that breeder technology could handle the day-to-day demands of the commercial grid. Engineers meticulously tracked every aspect of the core's performance. The stability of the U-233 fuel and the rate of thorium conversion were being validated in real time. This mountains of data would later become the most important legacy of the program, preserving the technical proof of thorium's potential for future generations. When the experiment concluded in 1982, the final assay provided the definitive proof that advocates had sought for decades. The results were undeniable. Scientists at the Idaho National Laboratory worked around the clock to analyze the irradiated fuel, seeking the single number that would validate the breeder concept. The final results showed that the core contained roughly 1.4% more fissile material than it had started with. Thorium breeding at commercial scale was no longer a theory, it was a physical fact. This success proved that thorium could sustain its own fuel cycle, potentially providing energy for thousands of years. It was a monumental achievement. Rickover and his team had shown that we could create more fuel than we consumed using the existing technology of the time. The report, titled Summary of the Shippingport Light Water Breeder Reactor Program, remains a cornerstone of nuclear research to this day, a testament to what was achieved. Despite the data, no commercial follow-on was ever funded. The window for thorium in the United States was already being shut, not by physics, but by a shift in national energy policy. The industrial momentum required to scale this success into a national fleet was systematically dismantled by political and budgetary shifts in Washington. By the late 1960s, a decisive political and budgetary shift had occurred. The U.S. government had picked its winner, the liquid metal fast breeder reactor. The Atomic Energy Commission had decided that the plutonium path was the only one that mattered, effectively starving all other innovative designs of the resources they needed to survive. The Atomic Energy Commission was single-mindedly focused on the plutonium path. For the commissioners in Washington, thorium was an elegant distraction from the main goal of rapid plutonium expansion. They viewed the LMFBR as the logical technical successor to the Manhattan Project's plutonium-based infrastructure, regardless of the safety concerns. The fast breeder path used plutonium fuel and liquid sodium coolant. It promised even higher breeding ratios than thorium, and it fit perfectly into the established industrial network of the Cold War era. This focus created a technological lock-in that made it nearly impossible for the thorium molten salt concept to compete for funding. Support for thorium and molten salt work was geographically and institutionally concentrated almost entirely at Oak Ridge. Without a broad base of industrial and political backing across other states, the program was uniquely vulnerable to budget cuts. While plutonium had champions in many states, thorium was seen only as a project for the hills of Tennessee. There were also real technical concerns that gave critics the ammunition they needed. The corrosive nature of the fluoride salt was a challenge that required a breakthrough in materials science. Critics within the AEC used these technical hurdles to argue that the molten salt design was too complex and too far from commercial viability to be worth the continued investment. Tellurium in the salt was causing microscopic cracks in the reactor's metal structure, a phenomenon that could lead to catastrophic failure over long periods. Engineers needed years of expensive material testing to solve this, but the funding was being diverted to the plutonium fast breeder. The battle of the materials was being lost not in the lab, but in the boardroom. Furthermore, the long-term behavior of the graphite moderator under intense radiation was another major open question. The graphite blocks would swell and distort over time, requiring periodic and expensive replacement. This added significant uncertainty to the economic case for thorium reactors, giving the AEC the justification they needed to finally pull the plug. But the most daunting hurdle was the requirement for continuous online chemical processing. To manage the thorium cycle efficiently, the reactor had to be its own chemical plant, processing the fuel while it was still hot and running. This level of automation and complexity was unprecedented in the nuclear industry and remains a challenge even today. Building and maintaining such a complex system in a high-radiation environment was a feat of engineering that many felt was decades ahead of its time. The sheer scale of the pipes, separators, and shielding required for a commercial-sized plant was staggering, and the industrial capabilities of the 1970s were simply not ready to meet the challenge at scale. Efficient breeding required the continuous removal of protactinium-233, allowing it to decay safely outside the core before being returned as uranium-233. This chemical dance had to be flawless, as any failure in the extraction loop could poison the entire breeding process and significantly reduce the reactor's efficiency and power output. Every pump and every seal was a potential failure point. The reliability needed for commercial power was a hurdle the 1970s team struggled to clear. This processing step also raised uncomfortable questions about non-proliferation. By separating protactinium, the plant would be creating a stream of nearly pure uranium-233, a material that could theoretically be diverted for use in nuclear weapons. This created a massive security and safeguard challenge that the AEC was unwilling to face in a commercial setting. Unlike low-enriched uranium used in most reactors, U-233 could theoretically be used in nuclear weapons, creating a major safeguard challenge for any commercial facility. While uranium-232 contamination made the fuel difficult and dangerous for outsiders to handle due to intense gamma radiation, the plant operators themselves would have a technical pathway to obtain pure fissile material. This insider threat was viewed as a major liability, especially during the heightened security atmosphere of the late Cold War. Weinberg's insistence on the safety and elegance of thorium had made him a political pariah. He had famously said that we could not afford to be wrong about nuclear safety, but the policymakers in Washington were more interested in the rapid expansion of nuclear fuel production than in the inherent safety of molten salt designs. In 1972, the program's most powerful champion was silenced. Alvin Weinberg, who had led Oak Ridge and the Thorium vision since the 1940s, was ousted as the laboratory's director. His dismissal marked the symbolic end of government support for thorium and the final triumph of the plutonium fast breeder faction within the AEC. Weinberg's insistence on the safety and elegance of thorium had made him a political pariah. He had famously said that we could not afford to be wrong about nuclear safety, but the policymakers in Washington were more interested in the rapid expansion of nuclear fuel production than in the inherent safety of molten salt designs. With Weinberg gone, the AEC moved quickly to wind down all molten salt research. Funding was slashed to near zero, and the specialized teams that had spent decades on thorium were dismantled. It was the end of an era of unprecedented innovation, as the most promising alternative to solid fuel reactors was systematically buried by bureaucracy. The research budget for thorium, which had seen steady growth through the 1960s, was now completely eliminated. The unique base of expertise, built through thousands of hours of experimentation at the MSRE, began to evaporate as scientists were reassigned or forced into early retirement. The loss of human capital was just as devastating as the loss of funding. The technology that promised a new era of clean, abundant energy was effectively shelved. It became a hidden secret of the Cold War, a vast collection of blueprints and forgotten technical reports gathering dust in government warehouses. For 30 years, the promise of thorium would remain locked away, out of sight and out of mind. For nearly 3 decades, thorium would remain a forgotten historical footnote, a fuel that almost was, known only to a few dedicated researchers and historians. The facility at Oak Ridge stood as a silent monument to a vision that had been remarkably successful in its execution, yet was ultimately defeated by political forces it could not control. But the data from those years was not lost. It remained the most comprehensive record of molten salt physics and chemistry in the world. This data foundation would eventually prove to be the most valuable legacy of the program, a technical inheritance that refused to stay buried despite decades of official neglect. That data would eventually become the bedrock for a new global movement. The kernel of truth proved at Oak Ridge in the 1960s was waiting for a 21st century audience to rediscover it. As the reports were slowly digitized and shared online, a new generation of engineers began to realize that the hard problems of the past were now within their reach. As the 20th century closed, the thorium community was just a scattered group of voices. But the physics remained as elegant as ever, and the momentum of history was about to shift again. The single light of this persistent idea had managed to stay lit through the long darkness of the great stall, waiting for the fuel to return.